All right, can everybody see my screen, this white page? All right.
Yes.
Okay, cool. All right, so we're doing today, characterization methods. All right, and we're gonna do NMR, which is an acronym for nuclear magnetic resonance. And we're also going to do infrared, which right, IR spectroscopy or infrared spectroscopy. So with the NMR, let me give you a basic like overview of that. So today we're doing what we call Proton Nmr or 1H NMR. All right, so Proton Nmr. And so what that's going to allow us to do for aspirin, and I'll show you all of the protons that are possible. Right, so NMR tells us about the carbon-hydrogen framework of a molecule. In other words, how the carbons and hydrogens are connected. And the way that you can tell how they're connected is the different what we call splitting patterns or multiplicity. And we'll talk about that. So let's point out the hydrogens on this molecule, right? So you have a hydrogen here, one here, one here, here, right? These hydrogens are going to give off a signal in the NMR based on the magnetic field around it, right? You also have a hydrogen here, right? And you have a CH3 over here. So these three hydrogens over here. Let me get a different color highlighter. Right, so in the aspirin NMR, we should see at least three signals. Right, you're going to see a signal for this, a signal for these three. And then for the aromatic protons, there may be some equivalents. So you're going to see potentially a signal for this proton, a signal for this proton. And then for these two, they may also give off a separate signal. So we're going to see at least three signals. Maximum number of signals we're going to see is 6. Because every proton is going to have its own signal if it's not equivalent. Right? So the 3 protons over here on the CH3, these are what we call homotopic. Right? What that means is that those protons are not going to generate separate signals. The signal that you see for that CH3 is going to be one signal, but it's going to be representative of all 3 protons. Right? The OH signal right here, the carboxylic acid signal, is going to show up way downfield on the spectrum, somewhere between 10 and 12, if it shows up at all. Right, so the NMR spectrum is in parts per million, and I'll explain more of this when we go down to the instrument. The scale is parts per million. It's calibrated from 0 using tetramethylsilane, sorry. And what it looks at is the different types of protons in a molecule. So you'll see what I'm not going to try to demonstrate the spectrum because you'll see what it looks like when we do it. So we're going to take 3 NMRs of 3 samples, and then we're going to take an NMR of the crude sample. All right. And so with the infrared doesn't tell you anything about the structure. The infrared is only going to tell you about the functional groups. All right, so infrared is going to tell you about the functional groups. So if you look at aspirin, you have multiple functional groups here. You have a carboxylic acid. And that's mainly going to be seen based on the actual carbonyl group. Right, so it's going to be this group that you see in the infrared that absorbs infrared radiation. And then you have an ester down here. Right, so you're going to see that ester show up in the infrared. That functional group is going to absorb infrared radiation. And then you have your aromatic system out here. So this is also going to show up as a functional group. So you have a ester, and then you have an aromatic, right? So those, and then there'll be some other stretches that you'll see in the infrared, but these are going to be the main ones we're looking for. All right. Any questions about anything? And after lab, if you go to Blackboard, there'll be an announcement, and it has a video discussing NMR and also discussing infrared in more detail. So it'll post to Blackboard at like 3:30 or something like that. I just didn't want to bombard you with announcements. All right. So let me stop sharing, and then we're going to prepare our samples, and we're going to go downstairs to the NMR. So there's going to be a little bit of a lag between when we set the samples up and when we actually get downstairs to run them. All right, and then we'll come back upstairs to do infrared, the FTIR. I can actually show you that though while we're up here. Just turn the camera around. So the FTIR, and these infrared instruments used to be huge, but modern technology saves the day once again. So this is an example of the FTIR. This is the instrument that we'll be using. And we're just going to basically put our sample here on this plate, and we're going to put a diamond tip over it. And that's what's going to, it'll be the infrared radiation will be coming through that tip and onto the sample, and it'll be absorbed by the sample. So we'll do this second, but we'll do the NMR first. So let me show you what we're going to do. All right, I have our samples over here. We're going to do 3 samples, and then we're going to do the crude, because what the NMR is going to tell us whether or not there's any junk left in our sample. We can kind of anticipate that because we already had the iron chloride test, and 2 of the samples were not so hot. 1 of them was excellent. And so we're going to find out today if there's any leftover acetic anhydride or any unreacted salicylic acid. We'll be able to see that in the NMR. So we have a NMR tube here. Just so I can get that in the. All right, it's just a little glass tube. And the way we prepare solids is we take a pipette, like so. I'm just going to go ahead and prepare the crude. And we just dip it into the crude and get a little bit of that material in the drawer. Right, you can see I have some material at the bottom of that pipette, and I'm just going to stick that down into here for now. All right, when we get downstairs, I'm going to add my solvent and dissolve this up. But for right now, we have enough material in here to get a good NMR spectrum. All right, so that's the crude. So let me move that out of the way. And I'm gonna give Tia, I'll give you this NMR tube right here, and then a pipette. So you're gonna be doing sample 1. So just dip the pipette down into that sample. No, you gotta dip it. You stirring. You think you making ramen noodles, chicken flavor, beef flavor. More, get a little more in there. All right, yeah, perfect. Now just sit that down in a tube like that, yo. And we're gonna put we need to mark that. So that's sample 1, yeah. Sharpie. No, it's here somewhere. All right, so just take the top off, sit that down in there. That way we don't get them mixed up. That would be horrible. To do all this setup and then mix the sample. So you're gonna take a sample of 2. All right, so we got another. We're gonna set another sample, mix up another sample. And this is gonna be sample 2. And when we do the NMR, you're gonna see the difference in these samples. If they're really clean, you're not gonna see any salicylic acid left over in there. Or acetic anhydride, which should have really been, take the top off the bottom. Be gentle here, because those tubes are fragile. And then I'm gonna set up sample 3. It's gonna take a little bit of 3. Not that much. Get off of it. What's that? Uh-oh. I don't wanna know. I don't want to know about your weekend exploits. No, okay. Oh, yeah. All right, so again, we got sample 3. We got enough aspirin. It may not look like a lot, but on the molecular level, that's plenty. So now we're going to make the trek downstairs. All right, so sorry it took more than a minute. But this is the spectroscopy lab. It's Armstrong 101. Over here we have a mass spectrometer, a QTOF, LCMS, highly sensitive instrument worth about $750,000. And then this is our NMR spectrometer. It's a 400 megahertz, and it better not be out. It is a Bruker. 400 megahertz, and it is worth about $275,000. So right now, we're going to go to the little command station, and before we do that, let me make sure I can get in here. I was already logged in. All right, so we're going to go ahead and take the samples and dilute them up. And this is Dr. Williams, by the way. You'll be on YouTube, so I'm warning you up in advance. Wow. So I'm gonna make up the first sample. When you do NMR, you have to do NMR in a deuterated solvent, right? So this is, let me get that on there. This is deuterated chloroform. Let me go back. All right, deuterated chloroform. Hold up, man. You didn't mess me up. My camera froze. All right. So this is deuterated chloroform, and the reason why we need a deuterated solvent is because in the NMR, within the NMR, there's a superconducting magnet, and that magnet needs something to lock onto. And so since we're doing proton NMR, we're using deuterium in the solvent, which is an isotope of hydrogen. And that deuterium is what the magnet is going to lock onto. It's going to lock the signal onto that. If you did it in a protonated solvent, then the solvent will be competing with your compound if you're doing proton NMR. So you got to use deuterated solvent. So I'm just going to take this. Let me Move this over here, that might be better, so I can see what I'm doing. You can see our NMR tubes with pipettes in them. So all I want to do now is just add some solvent to this to dissolve it up. Normally for NMR, you're doing 16 scan, and you want it to be about to here with solvent. So I'm going to add solvent to this. Hold it. All right. Absolutely. I'm just going to take this, and I'm trying not to drip this solvent. This stuff is super expensive. And I'm going to add the solvent directly to that pipette. That's the purpose of using the pipette to transfer the solid. I'm just going to add it directly. You can see now I have a sample that is ready to go into the NMR spectrometer. All right, add a little bit more and make sure everything dissolves up. All right, this is standard. You normally do about 2 centimeters. All right, just dump it on in there.
Is that good?
Yeah, that's fine. So y'all see her sample in her hand. Again, you want about 2 centimeters of solvent. So hopefully y'all can see that. So that's fine. And I think this is the crude. So you can cap that off. So you keep the cap on there.
Well, you don't like
I knew better than that. I knew better. I knew better when y'all said that. I knew better. And I still did. All right. So we're going to go to the software, which is Top Spin, which is down here. I think it's already booted up. Yeah. All right. And I don't think that there is a sample running. So what we have here up top, let me get closer. What we have here up top, these are all the processes to run a sample. So it's very user friendly. So we're going to go to File, we're going to go to New, and then we're going to select the experiment. We want to do Proton Nmr, right? What was up there was carbon NMR. We're not doing carbon. So we're going to go down and find Proton on the list. You see, there's a whole bunch of experiments in here. This is a very, very expensive and highly specialized instrument. So we just want to do a Proton. So I'm going to click Proton. Come on. All right, close. What are you doing? I need Proton. Come on, stop playing with me. I'm going to do Proton. All right, now, so you see where it says experiment. Hold up, y'all can't see that. You see where it says experiment. Now it says Proton. Now I want to change my solvent. I'm not using acetone. Acetone is one of the solvents you can use, but we're using CDCl3, deuterated chloroform. So we need that. I need to change the name. So this, I think this is crude. Or sample 3. I forgot the label. All right, so crude or 3, experiment number, process number, keep all that the same. None of this changes. All right, so we're going to just click OK. And now in the command panel, I need to take the sample out that's in there. So I'm just going to type EJ or eject. I need some room. I need a little elbow room. And you'll come over here. You'll see the sample pop up. Can y'all see that? There's a sample right here that's already in there. So we're going to take that out. And you see it, the sample is in a spinner. And the spinner kind of has a pattern on the top. That's on purpose. Because when you put this into the instrument, you have to spin the sample so that the radiation that's hitting it is homogeneous. It's going to hit it from every angle. So that's the purpose of that little checker, black and white checker boxes on the spinner. And the purpose of the spinner itself is to hold the sample up. And I don't know if y'all can hear that, but you hear that little hissing? That's compressed air. If you don't hear that, do not put a sample in. It's gonna drop straight to the bottom. It's probably gonna break. Probably gonna have to call the company. They start charging you from the time they get in the car to drive to the airport. So a normal repair like that will probably cost us about 50 grand. So if you don't hear the air, don't put a sample in. All right. So I'm gonna take this over to here. And I'm gonna take the spinner off of the old sample. And I'm gonna place it onto my sample, just like that. Right? But there's also a depth gauge, because it has to be at a certain depth so that the radiation can hit it like it's supposed to. I'm gonna sit it in the depth gauge like that. Right, this is the depth gauge. So I'm sitting the sample in there. Now I'm ready to put the sample into the spectrometer. I'm gonna come here. I hear that compressed air. So if I sit it there, it's gonna hover like it's supposed to. Right? And now I'm ready to inject the sample into the spectrometer. So I'm gonna go back to the command center, and now I'm gonna type in my command. I'm gonna inject it and not eject it. So I'm gonna type IJ. And now you'll see the sample go down. And you should hear it click. Right? Once you hear it click, that's when you know it's time, you can start processing. So I have my sample in, and you can see over here, right? This is my lock screen, and you'll see a little, you're gonna see it start pulsing back and forth eventually. The signal right here, it's not right now, but we're gonna lock on our sample. So right here, we're gonna click lock, and that's when it's gonna find that deuterium in the CdCl3. So we find our solvent, they can tell us to lock on that. And now you should see some action over here. Should. I'm not sure why it's not sweeping. But you can see right here that it's going through its, parameters, and it's gonna set the lock at a certain parameter, and then it'll be done. So now it says lock done. So then the next is to tune the probe. It's an auto tune, not like auto tune. So if I just click tune, you're gonna see it tune the probe to the sample, and you'll see it come up. You're gonna see like a parabola pop up, and it's gonna shift to where it's supposed to be. Come on. So normally, and you see it shifted back to the center. Normally, when we would tune a probe, you have to get underneath it with a tool, lay on the floor and turn it up and watch the screen at the same time. All right. But now with this, it's all user friendly. So it's tuned. Now you want to spin. So you want to turn the sample rotation on. And again, you spin it to make sure that the RF radiation is homogeneous. So you can see down here, it's going to show you down here, right here, that the sample is spinning. No, you can't see it. You don't want to see it. All right. So now that it's spinning, we want to shim it. What shimming does, there are magnetic coils inside this instrument. So when we shim it, what we're doing is we're homogenizing the magnetic field inside the instrument. So we're going to hit shim, and everything is automatic. Shimming used to be, back in the day, this gray panel that you see right here with that dial on the bottom, that used to be a real tactile panel that you have to turn the dial and watch the signal, and you shim it until the signal doesn't move anymore. But now shimming is all automatic, so you don't have to do that. But that was my favorite part. I felt like I was on a spaceship. I was pushing buttons, turning off. But now you don't have to do that, right? So it's going to shim automatically. All right. Any questions? Anybody got any questions while we're doing this? The shimming usually takes the longest, especially if the instrument hadn't been used in a while. Sometimes the coil, the magnetic field tends to drift, so you have to shim it up to make sure that magnetic field is where it's supposed to be. So it says shimming is finished. So now we just hit ProSolve. That's done. And to adjust the gain, just click that. Normally, and all of the buttons up here, you could type those commands in. This is all Unix programming language. So all the commands, you can just type them in, but everything is click a button. So now the receiver gain is ready. So this is the receiver. And that's now ready to receive data from the magnet. So then we just click go. And you're going to see it on the screen. What you're going to see is what's called a FID, free induction decay. And it's going to grow in over time. And it's going to look like a tornado turned on its side. That's the best way I can describe it. Right? So when that's going to keep going. And again, when you're running a sample for a Proton NMR, it's 16 scans. Right now it's on scan number 2. All right, so you can see it. Now it's on number 4. And after it's done, we can process it. All right, any questions while we're doing this?
Yes.
Go ahead.
I'm confused because like, are we going based off of I think it's the NMR assignment like
Yeah.
that? Are we going based
No, don't do that. We're actually running the NMR.
Oh,
the
so
NMR assignment is for later.
okay, so once we finish this, then we can get to
That's
that.
fine. Yeah, but we still need to do this too.
Okay, because I was
Yeah.
confused. I didn't know what I was supposed to be writing down.
Yeah, if you already did the NMR assignment and watched that video, that's fine.
Okay.
All right, so now this is the FID. This is useless to us because number one, it's in hertz on the x-axis. So we don't know where anything is. So we need to convert this. So we're going to do a transformation. So I'm going to type in the little window down here, TR. And then what kind of transformation? We're going to do a Fourier Transform. So that's FT. And you'll see this convert. So now I need to process this. And right now it's upside down. So I need to phase it, bring it into phase. So I just type in APK and I'm gonna bring this down. And I wanna blow this up. All right, so you can see, if I can get that over there, you can see signals down here in about, let me zoom in. You see signals down here between 7 and 8. Those are going to correspond to your aromatic protons on aspirin. So you can see 1, 2, 3, 4 signals. This is the solvent, right? So we're not worried about that. That's the solvent. And then I'm going to go down here. Here you see 1 signal right here. This is the TMS, tetramethylsilane. That's doped in with the solvent so that you can calibrate your spectrum. That always shows up as 0, right? So that's that. And then here you got you have a signal at about 2.4, right? That's good. And let me zoom out of this so you can actually see it. That's a very clean sample. This has got to be sample 3. This can't be the crude because there's no salicylic acid left over here whatsoever. All right, so this is pure and not crude. So this is sample 3. So I said crude or 3, so this is 3. So that means Taj has the crude. So once that's done, I want to click stop. right? And then I'm just gonna eject the old sample. And then we'll run another sample, right? It's the same for all of them. So that's clean. Sample 3 is super clean.
Mine's gonna be dirty.
All right, so type RJ, enter, and then go up this file, and you're gonna start a new file. New, you're going to export. I say new child.
Oh,
Change the name. You're doing sample what? 2?
1.
Sample 1. All right, so then click OK. Right now, go to lock, leave the lock, and then find your solvent, CDCO3, and click OK. Then go to the next function. No, click the button, not the menu button. Just click choose. You already locked it.
Right here?
If the lock is finished, it's still locked. So wait for that to finish, and then you'll click choose.
Okay.
Every command, when it's done, it'll show you.
Okay.
So now down there it says done.
Click.
And you click choose. Don't click any button until the previous command is finished.
I wonder who made this. It's super smart. Whoever made it.
You'll see the
Yeah.
tune again. That parabola is going to come up.
Is it done?
Nope.
Oh,
The parabola has to come up.
okay.
Did it come up already?
No.
Yeah, it'll come up. What does
Y
it
equals X
say?
squared.
Job succeeded? Yeah. Okay. All right, you can click spin now. It might have, since I tuned it on the last one, it might be faster because it's already ready for another sample. So click RO on.
This?
Yes. And you'll see it, the red dot, the red arrow come around that spinner on the screen. So right in front of it.
Oh. Huh.
Now you can stand over my shoulder once again.
I was trying to follow. I was trying to follow you. I was trying to follow you. But I was.
Now go to the
It's
next command, which is CHEM. Click. In that bottom left corner, that's where all your commands and all your functions are. Right there. This screen is all good.
Okay. It's so much. Like what?
Shimming always takes the longest, because again, you're gonna homogenize the magnetic field. You want to get good resolution. Without the shim, that last spectrum would have been all over the place. Would have been fuzzy looking, the peaks would have been merged together. You don't want that.
Okay. It says it succeeded.
All right, so go to the next command, which is console, just click this one. And that's done. Click game.
Is it possible for that to blow up? Oh. Oh.
It's possible for it to quench.
So who?
Quench. But inside it, it's liquid nitrogen and liquid helium. It's got a magnet superconductor, so it has to share a
Okay, it's done.
All right, so click go.
Go, go. Ooh.
Oh,
Ooh.
that company that has down like this.
Oh.
Back up or
Who?
oh, thanks.
Amen. Amen.
All right. So you'll see the FID, and it's the same for every sample. You're gonna have an FID coming up,
It's at 2 things.
and every proton NMR, we click that proton command at the beginning, that's telling you it's over 16, it's already pre-programmed. 16 scans.
Why can't it be 20?
You can do more.
Oh,
You can change any parameter. You
Okay.
saw all those experiments,
yeah.
like you can change any parameter.
Oh,
It's just up to you, but it's not necessary to do more than 16. You gotta concentrate on something.
oh.
The proton on the aspirin backbone.
Okay, see where it's at?
Yep. So when this comes up, I'll explain it. That's a good question.
Come on.
Relax. It's coming. It's only gonna move as fast as they wanna move.
Oh, it's done.
Beat.
It's done.
Is it done?
Yes.
So type, you know, you can't use that, right? So you need to transform it. So GR, hit enter, hit FT. Fourier Transform is just a mathematical calculation that's going to convert that graph into a readable spectrum. So go ahead. Okay, now type ATK. That's automatic phase, but it's in German, so that's what the K is for. All right. Now click the arrow. See the little arrows up here? Come over. Right there. Click the one up. Yeah. Scroll down. Hold the mouse button down, and just scroll that down.
Oh, press it.
Yeah. Press the mouse button. And pull the mouse back to you.
Oh.
Right there. Go up. Go up. All right. That's good. Now hit multiply by 8. Ooh, that's easy. Wow.
Uh-oh.
Go ahead, do it again. Okay, stop. All right. So those of you who are watching, if you see those peaks, each one of those peaks is going to correspond to, like I showed you earlier on the notes, the ones in the back between 7 and 8. So you zoom in, hit the little plus, magnifying glass, plus in, up to the left. Yep. A little bit more. Right there. Yeah. Turn that. Okay. Yeah, good. So each one of those peaks you see down there represents one of the hydrogens on the aromatic one. Because remember there were 4 hydrogens on there?
Yeah.
So they're all non-equivalent. So they all give their same signal.
Okay.
And then you scroll down, use the side-to-side arrow up there where you work. Yep. Just drag it until you get down right there. That peak right there is the CH3 peak on the ester.
Okay, guys, so we're gonna run sample number 2. We clean the stage. We make sure that is the diamond where you put the sample in is very clean. We're running a background for this sample, because basically you're running the sample in there. So you want a background of all the peaks for the moisture and carbon dioxide that should be taken off. Okay, basically we're taking off, subtracted out from the sample. So the peaks later on you're going to see will be the peaks only due to your sample. Okay, I'm not going to add the background. You're asking me to add the background to the page. I don't want that. Again, the software is going to keep it and subtract it. So I say no. Now it's a matter of putting my sample. Use a macro spatula because you don't need a lot of sample. You just need literally milligrams. I'm going to switch this to the right. And there is a small diamond window. That's where you need to take enough sample just to cover that diamond window. Okay. Move it a little bit with the spatula. Center it into that diamond window. And then you push your arm of your press. That's a press. Then rotate it. It goes down until it presses that sample against the diamond window to make it flat, as flat as possible, because you need the sample. So the beam of the IR should pass through it, so it should be as flat as possible. Okay, rotate it, then you see a torque, and it's going to stop rotating. kind of skip. If you skip, that means the sample is flat against the diamond window. Now is the next step is how to run the sample. This is the previous sample is already there. I'm going to say collect sample, and then I have to give it a name. So this is aspirin sample 2, and then I always like to put the date, just in case if I want to come and rewrite it again. I know what's different. Step 19 is today, and then say prepare. We always give you kind of a warning, because if you're not ready, we give you okay, prepare to collect the sample. I know I have done this, so I would say okay. They give you kind of a preview. It will take only one scan, give you kind of a preview of what is your sample is. Okay, then I'm going to indicate the start collection in order to complete going from only one scan to the total number of scans, which is 32. This is not as clean as that. No,
It's dirty.
yeah,
Yeah, it has some leftover salicylic acid in it.
yeah. This is not as clean as the previous one. That one is much more clean. But we'll find out when we can run it again. Is the library. It will tell us what does it happen. Okay. So you can see clearly the differences, right?
Yeah.
It's like one was the moment from the first scan, straight baseline. Here you see all of this going up and down. It means it has, as you said, it has impurities on it. So that's going to be a good point in order to compare between sample number 2, sample number 1. The baseline, you see, the baseline is not as flat as the first one is.
It doesn't mean it has salicylic acid.
That's what he says.
Corrode in it. You can tell that from the NMR. But the drawback
Actual. Go ahead.
of infrared is that you can't see what the impurity is.
Okay.
In the NMR, you can see it right away. You see 2 sets of peaks in the aromatic region that correspond to aspirin, salicylic acid. Here, you can't see them.
Yeah.
That's why this is not definitive. This is just like a method that you confirm what you have.
So-
NMR is definitive.
Here I'm going to add it to window 1, so it's actually going to show me a comparison between them right away. See the difference?
Big difference. More
Yeah.
aromatic.
This is the sample one is the blue one. That's one is just the more clear, and the red one is the sample number 2. Okay, so I need to clear sample number 1. That's all right. Go ahead.
That's aromatic stretching. The hydrogens and carbons on the ring,
Yeah.
like the bond is like a spring, right? So when you irradiate it, if the frequencies match, like the spring is moving at a certain frequency, then the radiation that hits it is the same, it's going to excite it. So it's just stretching, and that's what's being detected. So that's aromatic CH stretching.
I cleared the first one. I'm just going to run the comparison to the second one. It's the same thing as we have done, and hopefully it will give me. How did I do it? Remember? Oh, search right here. See that? Like kind of magnifying glass. Yes. So it gave me something. Yeah, it gave me. But you see, the match over there was so high. Remember, the match was about 70 something. Yeah, it picked up the peak for acetyl salicylic acid and aspirin in there, compared to the aspirin, but it's not as clean as they say it with other. So you see, it gave you like 3-phenyl toluene in there, benzyl chloroacetate, triphenylphosphine. Oh my goodness, yeah.
There's a lot of crap.
It's a lot. Yeah. Thank you. But anyway, run sample number 3. You want somebody else to?
That's fine.
It's fine.
The
You
sample
all
three is
got
right
the point right now. So you all feel comfortable doing sample number 3? Sure. Okay. Okay. So I'm going to move this so we don't get any confusion. Let's move that away. That's what I'm going to do. And now the next is you're going to do. Yeah. Screw. Clean it up. Clean it up. Okay. Take it and you can just dump it in here. I need to save that sample. Make sure that, see how it's the, look at the bottom. It should fit. See that one should fit right there. When you rotate it, it fits right there. Okay. Make sure to clean. Remember, this part also has soap. Yeah. I'm just saving the sample. And I set them. I don't know how I will be able to send them right now. We need to put some internet on this.
Oh,
We
yeah.
need to get the Wi-Fi so we can email the sample right away. So you clean most of them. Okay, clean most of them. Make sure to pick up this again. Clean one more time. Put on the sample on the bench. Take a small amount. Cover up the diamond. Okay. So let's try to see if this is there. That's it.
Yeah, this is gonna be a clean sample.
Can you move a little bit to the side so everyone hopefully they'll be able to see it? You just need to take any part of the sample, it doesn't matter. That's a lot, but that's okay. That's okay. That's okay. I was telling you if the advantage of the FTIR is non-destructive, so if somehow you ended up in milligrams of the sample, you can run FTIR and you can recover it and still use it for any other thing. That's good enough. Okay, you need to rotate the arm and then make sure that the press, the other way. Then it's going to keep going until you hear that click. Okay. So this is sample number 2. We don't need to run it. Just run it back around. You can just go ahead and collect sample.
Select the sample.
Yes, you need to run it out. You can just collect sample. This aspirin. Dash sample 3. And that's 10, 19. Okay. He said, okay, we did that. So give you. Yeah, that's also a good sample. That's kind of in between. The first one, the top one. You can go ahead and remember, it gives you only the preview. You have to hit start collection to go through the whole 32 steps. No. Just keep doing it. Yeah. So now it's going to go through the 32 scans.
Yeah, that's much cleaner.
Yeah.
You can see that right
It's
away.
better than, but that first one, whoever did that, did a marvelous job. Sample number 1. What was the solvent?
That we ran it in? Or
No,
recrystallized
the crystallization solvent.
ethanol.
Oh, ethanol? Oh, okay.
Ethanol. And
Oh, you synthesis? You're talking about the synthesis?
yeah, the synthesis was deep. No solvent.
Oh, okay.
The acetic anhydride was solvent.
Well, the solvent.
So yeah, that's a lot. That's a lot.
You can get a lot of good information from this guy. It's very good. So that's why we call it the quick and dirty. You can get very good information from this. Okay?
Well, I
You
tell
can
you
go
what,
ahead and hit add.
live wire. That's a live wire right there.
Yes.
Yes.
Pew, pew, pew.
It's pretty much very comparable. Kind of like, yeah, pretty much more or less. The red one is sample number 3 compared to sample number 2. Compared, I can open it and see. Yeah, I can open it and see. Okay, here we can see the difference.
Yeah, one is
One is the red
way-
one.
Yeah.
The sample one is the red one. Normally, the sample that's open is going to be a red.
Big difference.
Change other ones in order for comparison. The green one, sample number 2, and the purple one is sample number 2.
Yeah. But you can see the functional groups. Like you can see the functional groups, but there's a difference. Sample one is way cleaner.
It's very cleaner. Look at how
And the
straight.
absorbance is a lot stronger for your carbonyls too. You see how the red
Yeah.
Right
downward spikes are so much more intense. That's a good sign.
You can also say there's something I used to, but since you can say fine peaks, it will actually label the peaks.
Yeah.
for you.
Yeah.
For
that's
example,
important.
position other than finding it manually. you can show you. But all of this is safe. You can always save the spectra and come back and reanalyze it as much as you want.
Yeah.
Okay, so it's saved it as a raw data, and you can always analyze. So right now, show you exactly how much peak are in there, and then you can play and see, like, you don't want too many, because normally FDIR is very greasy, but you're really focusing into specific peaks. You don't want it to label for you every single peak.
Yeah.
Then you're gonna get confused. Okay?
Good.
We good? All right.